Hello, welcome to the course Essentials of Data Science with R Software 2, where we are trying to learn the topics of sampling theory and linear regression analysis. And in this module, we are going to continue with the sampling theory with R Software, and we are going to discuss the topic of simple random sampling with R Software. So you may recall that in the earlier lecture that how are we going to compute the mean, standard error of a sample mean as well as its variance and the confidence interval estimation in the R software. Now, the similar thing I will try to do here, but in the case of simple random sampling with replacement. So, most of the basic fundamental concept behind the computation I already have explained you. So, in this lecture I will try to be quick, because same concept, same rule, same notations, everything is same, they will be following here. Okay, so let us try to begin our lecture. So now I will try to create here the same population. I will try to consider the same what we considered in the earlier lecture, that is the numbers from 1 to 20. So suppose there is a population of size 20, which is denoted by x. Now I use the command here sample, and I try to draw here a sample of size 5 from this data vector, which is population here x, and here since I am using simple random sampling with replacement, so I will use here replace equal to true. So now this is my here sample which I have got when I was preparing my slides. So you can see here that these two values 18 and 18, they are repeated here. So they are repeated 2 times. Okay, now I will try to take here the first case when the population variance sigma square is known. Well, anyway, as far as you are considering the estimation of population mean by the sample mean, that is sample arithmetic mean, it will not make any difference, right? When you go for the computation of variance and standard error as well as test of hypothesis, then this will make difference. So if you want to estimate the population mean by sample mean, that means we are going to find out only the arithmetic mean of the values. So this can be computed by using the command mean of y. Y is my data vector that will indicate the sample values. And in case of simple random sampling with replacement, the computation of variance of y bar is pretty straightforward. Why? Because if you remember the estimate of variance of y bar under WR, this was S square by n, and in R this the command VAR, this computes the quantity small s square. Okay. So in case if you want to find out the standard error, then you simply have to take the positive square root of this command. So the variance of y bar, that is sample mean, can be estimated using the command variance of y divided by n, that is the sample size, and its standard error can be computed by taking its positive square root. So now we have this sample here, and those sample values have been stored in a variable YWR, and if I want to find out the mean, I simply have to find out the sample mean, that is mean of YWR, and this value comes out to be here 12.8. And if you want to find out the standard error or the variance of y bar, that is pretty straightforward. To find out the variance of y bar under SRSWR, you simply have to find out variance of YWR divided by n. So you can see here this value here is 10.94. And if you want to find out standard error, you simply have to take the square root of this value. So this can be obtained by the command SQRT of the same command which is used here. So this comes out to be 3.30 approximately, and this is here the screenshot. So as I said earlier, when I try to repeat on the R console here, then these results will change, because hopefully I will be getting a different sample. And when you try to construct the confidence interval, as I discussed in the earlier lecture, you will need here the value z alpha by 2. So, I will not discuss it here because I already have discussed it earlier. So, in order to find out the value of z alpha by 2, we simply have to essentially find the percentile. Those percentiles can be obtained using the command qnorm. So, for alpha is equal to 2.5% or 0.025, the qnorm will be given as 1 minus alpha. So, this will be qnorm 0.975, and if you try to execute it, this will give you the value 1.96, which is approximate value, and the same command can be obtained from the R on the R console also. And if you want to put this alpha to be 5%, then the value inside the parenthesis in the qnorm command will be 1 minus alpha. So, that will be 1 minus 0.05, which is 0.95, and this value comes out to be close to 1.64. Now, I try to compute the confidence interval, and as we had discussed, we have to compute the lower limit of the confidence interval. Please have a look in the bottom of the slide, and the upper confidence limit. So, for this, as I discussed it earlier, these things can be programmed very easily. Y bar can be obtained by mean of y, and this variance of y bar is obtained already, and then you have to use the square root. So, this thing can be written over here. You can see here I am writing here mean of y minus error ZWR, where error ZWR is z alpha by 2, which is here obtained by qnorm 0.975 for alpha is equal to 0.05, and the standard error is obtained by the command sqrt inside the parenthesis variance of y divided by n. Right. So, this will give you the second component of the lower and upper confidence limit, and if you try to just say mean of y minus this component error ZWR, this will give you the left confidence limit of the confidence interval. And similarly, if you try to write down mean of y plus this error ZWR, this will give you the upper confidence limit, which I have denoted by right CIZWR. That means right confidence interval of Z, that means under the normality under WR. So, now we try to execute these things over the R console. So, as we have seen that n is equal to here 5 small n, which is the sample size, and here practically you do not need here actually capital N. So, that is the reason that I am not giving it here, although if you wish you can give it, you know it, but in order to compute the confidence interval you need only the variance, and variance depends only on a small n. Right. So, you can see here I am writing here qnorm, which is the z value, and the standard error of y bar, and then I try to compute the left and right limits of the confidence interval using the same command, and you can see here this is my here outcome for the given data set. So, my 95% confidence interval for this capital Y bar comes out to be close to 7.74 to 17.86. Okay, so this is what I wanted to find, and the interpretation exactly goes in the same way as I discussed in the earlier lecture. Now, I try to take the second case where the variance is assumed to be unknown. So, sigma square is unknown. So, in this case we had used t distribution. So, for the t distribution I had discussed in the earlier lecture that the percentile or the quantiles of a t distribution can be obtained using the command qt, and inside the parenthesis you have to give the value of 1 minus alpha and the degrees of freedom. So, degrees of freedom, remember that in the confidence interval it is n minus 1, and here we have to give the exact degrees of freedom. So, either you write here in terms of sample size as n minus 1, or you give directly the value of n minus 1. So, if you try to take alpha is equal to 5%, then alpha by 2 will be 2.5%, and the 97.5 percentile of t distribution with 4 degrees of freedom can be obtained using this command, and similarly the at alpha equal to 5%, this percentile, the 95th percentile can be obtained using this command, and these are the values. They are the same values which we have obtained in the earlier lecture. Now exactly on the same lines, you can see here, this is here the confidence interval, this is your here the lower limit, and this is here the upper limit. And in order to compute it, so this value can be obtained by the command qt. This value y bar can be obtained using the mean of y, and this quantity square root of variance of y bar, this can be obtained by square root of variance of y divided by n. So these things, so this part which is here like here, this I am trying to compute here in this function error TWR, which is here qt, that is the value of t, and then I am trying to find out the variance and then taking its square root, and based on that then I try to compute the left confidence interval here like this, here in this command, which is here mean of y minus this error TWR, and here in the second one here I am trying to compute the upper limit of the confidence interval. That is pretty straightforward, it is not difficult. And then if I try to put it on the R software, so you may recall that our population was 1 to 20 and we had obtained a, and we are trying to obtain here a sample using SRSWR. So for that the command is sample population x size 5, and then now replace will become here true, because we want it by with replacement. So this sample is obtained here. So now this sample is here like this, and for this sample I am denoting here n equal to 5, and then I am trying to compute it. So I simply try to give it here the value here YWR in place of y, and I try to compute the error TWR part, and which comes out to be 9.18. Then I try to use the lower limit of the confidence interval and upper limit of the confidence interval by the usual commands. For this sample, this value comes out to be 3.67, and the right limit of the confidence interval comes out to be 21.98 approximately. So I can see here that the 95% confidence interval when sigma square is unknown to us comes out to be say close to 3.61 to 21.98. Right. So this is my confidence interval in this case. The interpretation goes exactly on the same way as we did earlier when I was trying to prepare this lecture. Now you will be getting a different sample, so these values may not match, but the expressions and formula will match. Okay, before I go further, let me try to show you these things on the R console itself. So if you try to see here, first I try to create here a sample here. On the R console, I try to define my population 1 to 20, and then I try to take a sample over here with replacement, and you can see here this is my sample. So you can see here this time 15 and 15 are repeated 2 times. Now if you try to find out here its mean, so it will be mean of YWR. So this is straightforward, this comes out to be 9, and if you want to find out the standard error of the sample mean, which is variance of YWR divided by here n. Right. So let me try to give it here first n is equal to here 5. So I try to find out the variance of YWR divided by n, which will give me the variance of the sample mean under SRSWR, which is here 7.9. And if I want to find out the standard error, then I simply have to take the square root of this quantity. So this is positive, so it will be always be positive. So the standard error is 2.81. And now if you assume that the sigma square is known, then in that case if you want to compute the confidence interval, then The error part is computed here by this thing. So, you can see here error, this comes out to be here NA. Why this is here NA? Because you have not replaced here y by YWR. So, you can see here now this comes out to be the correct value. And now, if you try to find out here lower confidence limit, let me call it LCI, that will be here mean of YWR minus error ZWR, right. So, this is here LCI, this is the lower confidence limit when sigma square is known, and if you try to find out the upper confidence limit, let me denote it by here UCI. So, that will be mean of the observation plus error ZWR. So, this comes out to be UCI, which is 14.50. So, the 95% confidence interval turns out to be 3.49 to 14.50. And now, similarly, if you want to find out the confidence interval using the T quick distribution here when sigma square is unknown. So, the error TWR is obtained by this command. So, you can see its value is like this, and if you want to find out the lower limit, so LCIT, let us call it LCIT lower confidence interval with T distribution. This is mean of YWR minus error TWR. So, this comes out to be here LCIT, and if you, which is 1.19, and if you try to find out the upper confidence limit, then let me call it UCIT. So, this UCIT comes out to be here 16.80. So, once again the same conclusion that we discussed in the earlier lecture holds true here, that lower confidence interval when sigma square is known is from 3.49 to 14.5, and when sigma square is unknown and it is being estimated from the sample, so it is 1.19 to 16.8 or so. So, that is obvious that that for the same sample, when you are trying to replace a known value by an estimated value, then definitely the sampling variation will increase in these quantities, right. So, the confidence interval which are constructed when sigma square is unknown, usually they will have their confidence width, the width of the confidence interval will be higher than the width of the confidence interval when sigma square is known to us. So, now after this I try to come back on my slides and I try to give you the last topic of this simple random sampling, which is pretty straightforward. Okay, so, now in this small topic I am simply going to give you an idea of estimation of population total. That is pretty straightforward actually. Sometimes in practice the people are not interested in the average value. They are not interested in estimating the population mean, but they want to find out the total. For example, I want to know what is the total of the population. For example, if I say yi is the height of the ith person, then I simply want to find out the sum of yi's over the entire population. Yeah, in some practical application this is of interest. So, here I would like to show you that there is a one-to-one correspondence between the estimation of population mean and estimation of the population total. So, in order to estimate the population total, you do not have to do anything new, but using the result what you have obtained in case of population total, they can be directly used here with a very minor modification. How? Let me try to show you in this slide. Okay. So, sometime we are interested in estimating the population total. For example, sometime we want to estimate the total household income, total expenditure, etc. But if you try to see what is the population total is defined as the sum of all the sampling units in the population. That means sum of all the units in the sampling frame corresponding to the variable under study. So, this we are going to denote by yt, which is I goes from 1 to capital N yi, and if you try to see, you had defined capital Y bar as 1 upon n, capital N I goes from 1 to capital N yi. So, this implies that summation I goes from 1 to here n, yi is nothing but n times y bar, right. So, this implies that yt is nothing but your n times y bar. So, using the rules of statistics, there is a one-to-one correspondence between the two parameters, which is yt and say y bar. So, if I know the estimator of capital Y bar, then I can obtain the estimator of yt directly using the one-to-one transformation. So, this becomes here because we know that we had estimated capital Y bar by small y bar. So, the estimator of total will become simply n times small y bar. So, this is what I am trying to show you here, that is y total can be estimated by yt hat, which is equal to n times small y bar. That means sample mean into the population size. And once you do this thing, then there is no problem in establishing the unbiasedness, because that will remain the same, because if you try to see expected value of yt hat will become simply n times expected value of y bar, which is n times capital Y bar, which is same as yt. So, there is no issue even under SRSWR and SRSWOR. This yt hat remains an unbiased and estimator of y bar, or sorry, y bar t, that is the population total. Now, in case if you want to find out the variance or the estimate of variance, that is very simple, because you already have established that yt hat is equal to n times y bar. So, whatever is your variance of here y bar t, that is same as n square times variance of y bar. So, this relationship I am going to use here, and so what you have to do, you simply have to multiply the variance of y bar under SRSWOR and under SRSWR by the quantity capital N square, and you will get here these two terms here, which are the variances of yt hat under the SRSWOR as well as under SRSWR. That is straightforward. And simply if you want to estimate these variances, because you can see here we have here capital S square, that is unknown in real data set in practice. So, I can find out an unbiased estimator of S square as we have done earlier, and actually we already have found the estimates of the variance. So, the estimate of the y hat t, mean the variance of the y hat t will be same as the variance of y bar hat under SRSWR and WOR. The only difference will be you have to multiply it by here the quantity capital N square, right. So, if you try to and see here that these are the expressions what we have obtained. So, that is pretty straightforward, right. So, now and similarly if you want to compute the confidence interval, means you can do it very easily, and that is straightforward. So, now I stop here, and I will also try to complete the chapter of simple random sampling, but this was simple random sampling for quantitative variable. I have not told you, but we always assumed that whatever y1, y2, yn we have taken, they are some quantitative variables. They are not like qualitative variables like as yes or no, low, medium or high, but they are taking some numerical values. So, this is all about the simple random sampling for quantitative variables. What to do with qualitative variables, that will be our next topic. That is not difficult, because once you have understood the simple random sampling technique, I will try to establish a one-to-one correspondence between the quantitative variable concepts and qualitative variable concepts, and that will make your life very simple. So, now this is your turn. I have completed this part. You try to take some example from the books, from the assignments, and try to practice them. Whatever I have taught, that is directly applicable in any bigger data set which we try to consider under the purview of data sciences. There cannot be a situation in data sciences where you would not like to estimate the population mean. There will not be a situation where you would like to find out the standard errors. There will not be a situation where you would like to find out the confidence interval for the population mean. So, be confident that these things are going to play a very important role if you want to become a data scientist. So, you practice, take your ambitions forward, and I will see you in the next lecture. Till then, goodbye.